Another physics video presentation. Sort of a challenge video. Baldy Catz, a YouTube personality of some kind. Whatever, a flat earth debunker. One of these physicists who mocks people who say things that are stupid, which is okay with me, frankly. People shouldn't be allowed to remain ignorant and full of crap and all that stuff. So very good. Debunk loud mouths who are saying things that are just really dumb. Fine. But I'm arguing that regular physics says things that are really dumb. I mean, like a big part of your physics, okay, your whole entanglement thing and this bent space thing and this time dimension thing. And I said entanglement, right? Simultaneous events aren't simultaneous because somehow if I change where my point of view is, I've changed reality. These kind of implications, anyway. Your conventional physics implies a lot of things, and it directly states things that I don't think you've come anywhere close to demonstrating with any evidence that they're true. And so, he says I misunderstand, and that's why I don't get the brilliant physics. But he doesn't demonstrate how I misunderstand. And so I'll just deal with one of the arguments about how photons do whatever, wave interference. First, the argument that they're waves, and then second, the argument that they ever interfere with each other, that a force, which photons are, ever interacts with another force in any way that could be detectable by a human being or the universe itself. So let's talk about beam splitters. So they have a whole story about how interferometers work. And the story is sort of dependent on some kind of the notions they have. They don't fully understand what polarization is. They might fully concede that the idea of the size of a wave, how big it is in space, right? The waves, see, they don't think the waves do this. They sort of know that it doesn't go every direction. They sort of know that, oh yeah, sometimes it just goes like this. Okay, the wave it doesn't going everywhere. So like a gamma ray or a photon isn't really going everywhere, like a big giant wave going everywhere. That it has a confinement called its polarization, a certain thickness. And I've come to the conclusion that that's a 2,000 atoms worth for the average visible light, something in that range. And that somehow this wave has this dimension, and that somehow something with this size, it's rather huge dimension, somehow wobbles some electron somewhere. So electron is connected to a proton in an atom, and it's supposed to be spinning around at preposterous speeds, and somehow it wobbles, and that creates a new photon. And that's all we get as an explanation. Somehow this big huge thing hits one tiny electron, something, 20, 40, 50,000 times smaller. It's probably smaller than that by their dimensions of how atoms are constructed. It's a tiny, tiny thing, maybe 1,000,000 times smaller than the size of this wave. And somehow this wave compels this electron to create a whole new one of these giant things. That's thousands of atoms across. All right, I'm saying, well, that's sort of rubbish. Okay, and all right, so to the more pertinent argument, they have a thing called a beam splitter that they use more than any other kind anyway. And it's a half-silvered piece of glass. Now they say half-silvered, which is a lie right from the start. Okay, so the idea is you have a piece of glass and then you put little dots of silvering on the back. So there's gaps between the little dots. And this, when light goes in, half the beam, well, that's not a very good line there. We'll fix that. So we can do that. For such brilliant performance artists. Okay, so the beam goes in, and half the beam, 50%, goes this way. All right. Well, that's readable enough. And the other 50% goes this way. Okay, and they just leave it kind of empty like that. They don't give you any details about this at all. So the first thing logically you can understand is the glass surfaces reflect light. So the first problem is that some percentage of the light is going to leave that first surface. Okay, it's going to hit the surface of the glass and just bounce off. So whatever that percentage would be, we could say 20% at a 45-degree angle. Okay, is 20% of the light just going to reflect off the first surface of the glass. Then you got the problem of the second surface of the glass. That another percentage is going to hit that. So you go back here, and as it goes through the glass, the 80% that's left, another 20% of that is going to be reflected off the bottom surface. So whatever 20% of 80%, which would be another whatever 10%, you could say. So the glass itself is probably going to create somewhere between 20 and 30% of the light is going to just reflect off glass. We haven't got to the silvers yet. Right. So it isn't half silvered. It's obviously has to be a lot less than half silvered, because now we got whatever it was, 80% of the light gets to here, and then 80%, and you lose another 10, so you only have 70% of the light is actually going to get to the silvered surface. And so you only want to reflect 30%. So this will be a lot less than half silvered. So that's not even the truth. And you have an extra complication is that at these angles, the light can end up internally reflecting. That is, some percentage will bounce back here again and come back out. And another percentage will bounce off the front surface and back and back and back, and you'll have internal reflection essentially. And that accounts for, you have this ringed pattern that's the end product. And that's sort of shown in this example in the sense that the pattern doesn't have to be rings. It can just be bands of light. Now, the fact is they call this an interference pattern, but the truth is that the white parts, light, are much bigger than the dark parts. So it's clearly not an even distribution of light to dark with photons. There's just, it's quite apparent that the white bands are bigger than the dark bands. So that's one irregularity never explained. The fact that they have a consistent brightness in some circumstances. Now in this pattern, the brightness does diminish as you go out. So the bigger the ring, the less photons, the less bright. And in the center being the brightest. And the center turns on and off as you change distances, and so it's basically telling you that you're creating on and off, on, off, on, off, and that's all. Just on, off for now. That's all you need to know. And this is essentially the focus of the interferometer. It doesn't pay, when people are doing the experiment, they don't pay any attention to this stuff out here. They just focus on this center and turning it on and off, on and off. And that's telling you the wavelength of the light, essentially. They're changing a full wavelength to go from on to on to on to on. They're changing the distance, the phase. All right, so back to the this. Okay, so how it's so thoroughly underexplained. So anyway, you're supposed to believe that these photons that go through all this percentage of degrade, is it degrading the actual photons? Do the actual photons get knocked into pieces? Or do the actual, are the photons themselves, like one whole photon goes this way and one whole photon goes this way? So that's something they're pretty unclear on. I mean, they're implying clearly that the whole photon goes in one direction and the whole photon goes in another direction. Now they end up calling them, once they get past these reflection points, once they get to this thing, then they'll call it some sort of wave function. It'll change what it is. So the photon somehow does do some kind of transition. So anyway, just pointing out that the beam splitters more complicated than what they just say. It somehow creates two equal beams going in these two different directions. The obvious thing I'm going to try to point out is that there's no way they can be called equal in any sense, because they're going to be doing two fundamentally different things. So we already know from their physics, some reliable experiments, you could argue well-established theory, is that anytime you force photons through a structure, some sort of impediment, whether it be a solid impediment or whether the impediment be something you're forcing them to hit and go around, or whether it's something where there's a gap and there's edges, surfaces, that photons always diverge. That is, they can end up over here, here, here. They can end up in lots of different locations because they are diffracted. They are, they call it that anyway. And the idea is that somehow, well, I've already pointed, see, I hate to mix these experiments, but you can't really help it. So, I mean, if Baldy Catz can give a good explanation for why exactly in their theory two waves are created, two wave functions are created, like what exactly causes that? Not some mathematical formula you can make up, okay, that just establishes the fact that there are two, but no, what exactly causes it? Because water just does this. Water doesn't create two waves. There's no interference in a single slit water experiment. Okay, you have a little bit of diffraction at the edges, and that's just caused by the fact that the wave can't get through. The cleaner the wave in, the cleaner the wave out. So if you can make a nice clean wave, just like throwing a stone in water, you won't get any interference pattern. A single stone thrown in a pond, and you get a nice, clear, straight one wave. That's all you get. One wave that goes out. No interference whatsoever. So if you could explain that, that would be a nice little extra bonus. But the point is that we know the light spreads, essentially is the word you could use. It spreads. It diffracts. So we know that with this example, so we've gone through the obstacle course, the first layer of the glass, the back layer of the glass. Now we're finally getting to the silver. And so the silver has to reflect what's left, like the 20% you need to finish it, or the 25%. So there's 25% silvering. So some of the light hits this pieces of silver, and, well, this is the tricky part, right? It has to go back through the glass again. So it's going to be not a full 30% or whatever the ratio of that stuff is. You're going to end up with the same problem. The light's going to hit the silver, and now it goes into the glass. It's going to refract, and then it's going to internally reflect, and it's going to do all the same things, and some of it's going to come back out, and some of it's going to end up going out this way. So some of it's going to reflect off the silver, end up reflecting off the glass, and then ending up going through one of the little holes between the silver. So you're going to have a little percentage, I don't know, 5%, some kind of small number, no doubt, of the light that's going to go through. Okay, this is the light going through now. It's going to go through when it actually did hit the silver, and it's actually going to reflect back and come back out through one of the holes in the silver. Now all these things have to be understood as path lengths. You see, each one of these is a path length. So this is a certain distance that the light has to take. So if it was a bullet, if I was just shooting a bullet, you'd understand that, okay, this bullet is going to be the shortest distance, right? I mean, this bullet is going to get here, okay, with this line. But this bullet, the one that goes through and reflects off the bottom surface, well, we have this whole extra bit that's been added on. So the second bullet is clearly going to have to travel a longer distance. And the other catch is this bullet inside the glass is going to move slower, 40% slower. So that's going to even add a little more distance. So the second bullet's going to be traveling a lot longer distance. And at a slower speed, which will look like a longer line if I just make them vectors. So these is where you're catching your wavelength differences. These are differences in time. So if the bullets start off at the same, they start off being flying through space at the same speed, right, aligned with each other at the same time, and now it's going to end up that one bullet Okay, this one's going to be the one that's ahead, but let's just do it for the sake of argument. The bullets aren't going to be in the same alignment anymore. They're going to be changed in their phase. So where they were in the same phase, now they're going to be way out of phase. And they could be out of phase by a whole wavelength or a wavelength and a half, or lots of variations. But the point is, there'll be lots of variations in the photons going in. The photons will be going in this way and this way, so there'll be lots of different path length differences. And the truth is the only one you're going to see in the end are the ones that are the same path, the ones that have the right wavelength difference in their, how far the bullets are off, are the only ones you're ever going to reconstruct into a photon. The underlying argument here is that there is no such thing as destructive interference. There's just constructive remaking of photons. You put bullets back in phase. You knock them out of phase by doing this, and then you put them back in phase when you hit them on a screen, and some of the ones from here match the ones from here and match the ones that came in this way, because the path lengths end up being the same and their phase ends up realigning. But anyway, let's continue the argument. Alright, so first, you can see there's a lot of complication in this beam splitter. It's not just doing some simple thing. It just says half the light go this way, half the light go that way. It's much more complicated than that, and these path lengths are incredibly different. So you can say, alright, so I've already demonstrated that these two are different. Well, obviously the one that reflected back again and then went through, that's an even longer line, okay? And clearly the one that goes in, bounces off the surface, hits the mirrored bit, hits this surface, and then goes through the hole. Okay, so that one's going to be a different phase. That one's going to be a different length of line, and you can just repeat that. So how many reflections it takes before it goes through a hole is going to determine how long the line is. So the point is, there's a whole bunch of different phase differences in the bullets is going to be created. You're going to create a whole bunch of frequencies, so to speak, because each path is going to have a different length to it. And it's going to take longer and longer for the bullet to get to point B. You could say some point B would be some straight line here, and the photons coming out are going to come out, the little bits are going to have very different path distances through a medium that slows them down. It takes them longer to get through it. Let's not say slow them down, because the truth is it just takes them longer to get through it. So anyway, after all this, so we know that the light that actually does go through one of these slits, consistent with what has been done over and over again, putting light through apertures, small apertures, we know the light that goes through the slits is going to be doing something extra weird, which is all of it's going to be diverging. So it's going to be spreading. So the light that reflects won't be spreading, because it didn't go through any slits. It'll just have lots of phase changes. So there'll be lots of out of alignment, timing problems with the light that reflects. And the light that goes through, not only is it going to have lots of timing issues, but it's also going to be spreading. All right. Now, in the case of, is that clear enough? Yeah, that's probably clear enough. In the case of the LIGO experiment, I really do need to erase some of this to kill this over here, and we'll kill this over here, because I think that's all understood. And then we have to wait for this to dry. Yeah. It's really hard to get the chalk to cooperate on wet board. It makes it really permanent. So, heard any good jokes lately? No, I guess we won't wait. I'll just reiterate the point. So the light that goes through the slits is going to have lots of phase changes, and it's going to now have directional changes. But something key to understand is that there is a truth to it. It's not just some random thing. There are photons that go right through the slit. That is, the substance of the photon is able, the pieces don't interact with the slit material, the surfaces, very much. So in truth, in real physics, see, their physics says there's the same chance of deflecting if you go in here or if you go in here. It doesn't matter where the photon goes through the slit, there's the same chance of it being deflected. And I would argue now, just like water, the ones that go through the middle do something very different than the ones that go by the edges. With water molecules, the ones that go through the middle retain their speed. The ones that go by the edges end up slowing down from friction, so they go much slower. And that's what actually creates the idea of different directions. Now in water, it's a bunch of stuff, but here we're talking about one single photon, and so we know the bits are not going to be, there's no such thing really as one single photon. You're just really taking a bunch of energy, and you either can construct a photon out of it or you can't. You either have enough of it in various phases to line up correctly, okay, to create a photon. See, I would argue a photon is made of little quanta, little bits at a specific distance from each other, all moving the same speed and out of alignment by a little bit. So the higher the frequency, the less out of alignment, but you know, it's a simple argument made many times. So anyway, so the truth is the two beams, ruin my good space. You can understand like in LIGO. So LIGO uses this half-silvered mirror. Now, even though there's just no way these two can be the same, so let me just draw the picture of it. So here's the beam splitter. We are sending light into it. We're reflecting some off of it. And then the stuff that's going through, as I just pointed out, is also doing this. It's diverging. It's spreading. And now it's going to bounce off a mirror, and it's just going to keep spreading as it bounces. So 1,600 times they send this light back and forth, and it's spreading the whole time. Now I would say the trick is that there are some photons that did make it right through the middle. And so there are some photons that are not diverging. And essentially what the interferometer is going to do, it's going to separate those out. All the ones that are going on one of these crooked paths, all of those are going to be invisible when they bring this beam all the way back and do the exact opposite, right? So they're going to reflect a new beam, and it's going to come out this way. You know, is that the way it comes out? Yeah, this one bounces off, goes back through, this one bounces off. Okay, so your output that you're going to look at, okay, so you're going to be looking at this picture and saying, what do I see? Okay, come back out of the beam splitter. And the trick is that one beam, most of that beam you'll never see because it's spreading so much you'll never get into your eye. So it's been eliminated, and the only light you'll get back is a little tiny bit of light, the tiny percentage of light that went straight through this little openings. So it never bent. So it's going straight. And the other beam, when it comes back, okay, it went back and forth 1,600 times, but it wasn't diverging much. So a big percentage of that will be able to get through, and it now has to go through the silver. So now it has to go through the little openings to get back. And all of this is still going to happen, all of these new phase changes. So on the trip back, all these phase state changes still happen. So there's lots of changing of the ordering of the bullets again. They're all getting, some are getting slowed down, some are getting more affected than others in terms of their path differences based on the fact of how much time they spent in the medium. But anyway, so all that's going to happen again, and there's going to be now the final, this beam diverged the whole trip, so a lot of photons got wiped out, and this beam is now going to diverge, okay, but it's clearly not going to be nearly as much because it's not traveling as much distance. So because it's so much less distance, it's like one beam diverged the whole trip, and the other beam's only going to diverge a little bit here at the end. So it would be a tiny difference in the amount of light that has been essentially destroyed by spreading it past your viewpoint, past even the mirror being able to reflect it. So they always do get a tiny bit of light back. So LIGO shoots, 10 megawatts or whatever of, energy through the device, and only gets back a tiny percentage of that, 0.01% or something. It gets a tiny number of photons back compared to how many it shot through the device. All right, so what you're really doing now is you're mixing a beam that's clearly going to be this beam has got to be stronger than the one that went the other way, just because it's diverged for less distance. But anyway, those are the two you're mixing. And I would argue that's all you're doing. You're just mixing two beams. You're mixing the little bullets that went through one process, and you're mixing the bullets from the other process, and they were both changed in their wavelengths and their distance between each other, and you know, and you're just going to say which ones go back to lining up. Okay, after that process, which ones have the right frequency to be seen, and you'll see them in the right location. So if you only shoot red light in, there's only certain locations where the path lengths for that frequency will end up making light, and so that's what you'll see. And so what we're really talking about is that little inner circle, and again, the inner circle flickers on and off based on the wavelength. And they say they can tell, well, okay, there's just a tiny number of photons, because it's in a spot where none of the bullets line up, and that's when it goes dark. But when the bullets start getting, the path lengths end up being the same as one wavelength, then it reconstructs a photon you can see. And so there's this graduation between being on and being off. And they say they can calculate, you know, within millions of little ruler lines, so to speak, they can detect a tiny bit of on, a tinier bit, you know, little tiny bits of onness. You know, like there's just a couple of photons that got reconstructed. Now the other problem is that theoretically, so these are just theoretical problems. So you have the theoretical problem that it can't be an equal beam because one beam's diverging through the whole experiment, the other beam only diverges at the end, and that's a fact caused by what slits do. So they can't undo that fact and pretend it doesn't cause that effect, because they know it does cause that effect. But the other problems are all of these refraction issues and the fact that it slows down in the medium and it changes the phase. So all you're really doing with any of these devices, a polarizing film, thin film that causes that little striped pattern, all you're doing is changing phase. Okay, you're breaking the phase of the photons. You're not absorbing the photons. You're not killing the photons. You're basically just saying the photon needs to be this. I mean, your wave has to be a consistent wave, if you want to think about it, a wave. All right, it has nodes in certain locations. If I change that, if I make one wave big and then I make this wave small, okay, where it's just a little hump here, and then it goes back to being a big wave again, no device we have can receive that out of frequency. The frequency has to be consistent. It can't be lines that are different distances apart. It has to be lines that are the same distance apart. The wave has to have a perfect continuity, or we can't see it with any device we have. It's just heat then. It's just noise. It's not a photon. So if I put another little line in here, it can't be received as a photon, a visible photon, because it has the wrong frequency. It's not consistent. It has to hit consistently at the same frequency to be recognized as a photon. All right. Probably more dependent not on having these little extra bits in, you know, a smaller frequency, but actually this line being further. So it's probably more about having a bigger empty space than an on space. So that's another reason why I'd understand that a photon isn't some kind of wave. It's an on and an on and an on. And what you're really doing is measuring the off distance. That's telling you what frequency it is how long is there nothing. The space between the quanta is telling you what the frequency is. So technically, possibly, a photon can have extra in it, be perceived as either this frequency or this frequency. But anyway, I don't want to get into that. That's a little more complex an argument. Alright, so what's the other point I wanted to raise was the mirrors. Okay, so the idea of the interferometer is the sending it back and forth. Like I said in the LIGO example, it goes back and forth 1,600 times between the mirrors, just going back and forth, back and forth, back and forth. And they know physics. You know, they know that even their most perfect mirror, it could be anywhere from 5 to 15 atoms. That's for the best they can do. That the light will travel and not hit, it'll travel a certain depth into the material, and less depth another time. So each time it hits, it's going to hit an atom that's could be 5 or 15 atoms deep into the surface and come back. So the actual dimensions of this mirror are never perfect. So each time, each 1,600 times it goes in, it's not consistent with this line anymore. The line's going too far, it's going less, it's going further, deeper. It's wobbling each time it goes in there. It's creating more noise to the signal, less perfection in this length of this line. So they have this idea that they're measuring distances, but each time they go through into the mirror, they go in a different distance. So how can you say, like, this line is this long and the other line is just a hair longer, coming back through? So one beam goes through the interferometer, the other beam goes, one beam goes one way, one beam goes the other way. They're really just measuring the distance between the beams, they claim, but there really can't be, because obviously the distance between the two beams would be screwed up 1,600 times of irregularity for both beams. Both beams are creating a whole bunch of noise, and their end result can't possibly be reflective of the wavelength of the light anymore, because the amount of distance they went into the material of the mirror is different each time, and that distance is greater, a lot greater than the distance of a proton. They're claiming they can measure a distance that's 1/10,000th of the width of a proton. Well, the distance they're traveling in and out of the mirror each time is many thousand times bigger than a proton. So how can you introduce that much noise and still claim you can see something that small when your lines have been changed in size by gigantic amounts relative to 1/10,000th of a proton? I mean, there's just no logic to it. You've got atoms worth of distance, right? And you're saying you can measure the distance of a proton, and you've got atoms worth of difference in the length of the two lines. So it theoretically doesn't make any sense. All right, but anyway, so he says, I misunderstand because I claim it can't possibly be what they claim. There's no big wave that goes in, and the wave goes in all these directions. The fact is that each photon, is made up of constituent elements. The more logical, I won't say the fact is, but the more logical way to view it is that each photon is made of constituent elements, and the fact is that it has a ray length, a duration of bang, 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 bullets being fired. And the truth is there are a little bit out of alignment, and the truth is that each one of them is going to interact with a different electron, and each one, by interacting with different electrons, is going to be sent in different directions by amounts that are standard to the pressure of the electrons. That is, however well bound the electron is going to dictate how much of a deflection you get and the momentum of the electron. And so each little quanta will give a certain momentum. The electron's in a certain tension and will cross a certain degree. So whether it's 3 degrees or whatever number you want to make, 3 degrees. So every time it hits an electron, it can get bent 3 degrees. So that's why it's always standard. Like it's either 3 degrees or 6 degrees or some other number. And all you're really doing, in the end, is breaking all these pieces up, sending them in different directions. So you're doing two things to these photons, these bullets that are in a row. You're changing their position. That is, you're taking one that was here and you're moving it here in time. So now there's two of them here and there's no photon, there's no quanta there. And you're sending them in different directions. That is, you're taking this polarization that's a certain size, and now you're sending pieces. One piece goes over here, one piece goes over here, but the pieces always go by a standard angle of deflection. So one photon comes in and he sends it 3 degrees, the other photon comes in 3 degrees, and so you can understand that at the locations on the screen, there's a whole bunch of this stuff hitting. It's hitting where there's no light, it's hitting everywhere. It's hitting the whole surface. But the only ones that can take, where you can take two different photons, you know, pretend this is a photon and this is a photon, this is a stream of bullets, this is a stream of bullets. And what you're doing is saying where the path lengths are one wavelength, you'll put those back in phase, and now that they're back in phase, they'll create the correct pattern, the right bullet order. So when you throw the bunch of bullets there, there'll be some of them, they'll turn back into a consistent frequency, and that's where you'll see a little, you know, you'll see a photon. You'll see a photon reflect, because the right energy hit at the right frequency, but it hit from more than one photon, coming in from different angles that have the right path length difference. And where the path length difference can't be reconstructed because the angle is wrong, there won't be any photon. It won't make any, you won't reconstruct any. So you'll just have heat here. You'll just have energy hitting, but none of the energy will be in the form of a visible photon. And then you'll be back to a spot that'll go light, and then it'll go dark, and then it'll go light, and then it'll go dark. But so there's never any destructive interference. Photons never communicate with each other. The little bits don't communicate with each other. They don't hit each other. They don't do any of that nonsense. Their energy, you either put a photon back together or you don't. You either get the phase back in the right order, so you can put different pieces together. You get a one wavelength difference in how much change there has been in their paths, you know, how much time they spent inside the slower medium. You either compensate for that in the sense that this extra time exactly equals at one wavelength when you come from two different locations, or it doesn't equal that one wavelength or two wavelengths or three wavelengths, so the phase isn't put back in order. The bullets aren't put back in the right order. But there's no destructive. There's either you make a new photon or you don't. So anyway, so tell me where I misunderstand. Show me where I'm the one not providing enough detail or getting to the real root of how the thing works. You just provide this simple nonsense that the beam splitter creates two equal beams when it can't. And then you say these beams somehow recombine and interact with each other through some wave function, and just magically produce a photon or no photon. Well, I'm going to argue the quanta is still there, and if you did the experiment, like the two-slit experiment, and you measure temperature instead of visible light, you'd see that there's the same amount of energy hitting all the locations on the screen. You haven't the light has spread evenly across the whole screen, and all you're saying is where can I make a visible photon? The energy's still there. You just can't see it because it's not in the form you can see. And so prove me wrong, so to speak. Show me how your superficial explanation is more correct. Your superficial explanation that relies on some magical wave function that creates two magical waves where only one wave is created, all of that stuff. Anyway, so that's most of the argument. And yeah, you have to know some physics to be able to deal with the points raised, but so what's the counter argument? How do you defend the argument that the beam splitter creates two equal beams? Not really possible. And such. And we'll call it a video. Until the next time. And such.